This is your Benchmark 2 review. You can access this review, this presentation, and a video review at www.srhschem.wikispaces.com. Here's some things that you will need in order to follow along with this video review. First, you're going to need your notes, that is note packets 6 through 9. You're going to want to have a paper and pencil so you can take notes. You're going to want your review packet so you can follow along, a table of elements, we are in chemistry, and I recommend that you have some post-it notes so you can write questions as you go and stick the notes to that topic. That way at the end of class I can answer any questions that you may have. First section that we're going to work on is the section about the mole. First question, a student has 1 mole of iron and 1 mole of lead. I want you to explain why both samples have the same number of atoms. Well, first, let's talk about a dozen. A dozen is always 12. It doesn't matter if it's a dozen eggs, donuts, people, whatever. It's still always going to be 12. A mole is similar to a dozen in the sense that it's always going to be the same number. So a mole is always 6.02 times 10 to the 23rd. It doesn't matter if it's a mole of eggs, donuts, people, iron atoms, or lead atoms. It's always going to be 1 mole, which is 6.02 times 10 to the 23rd. So there's some lead. And here's some copper. And oh no, it's the woolly copper bat. It will get you if you do not take notes during this presentation. Next question asks us about what units molar mass has. So, molar mass is how many grams 1 mole of a substance weighs. It's kind of like they took and counted out 1 mole, that's 6.02 times 10 to the 23rd, atoms or molecules of that substance, put it on a scale, and weighed it. So, molar mass always has units of grams per mole. Now, I do want to point out that in this case I have an X. That's because this number can change. It depends on what we're finding the molar mass of. So if it's the molar mass of HCl or NaOH or whatever, it's found by adding up the mass of each of the atoms in the compound from the table of elements. So you add those up, and depending on what the compound is, obviously you're going to get a different number there. But the units on that molar mass are always going to be grams per mole. Next question, how many grams does 1 mole of potassium weigh? How many atoms are in that 1 mole? So, 1 mole of potassium is 39.098 grams. How did I know that number? I looked at the table of elements and I found potassium, which has the symbol K. So that's how many grams are in 1 mole. All of those masses on the table of elements are assuming that I have 1 mole of atoms of that element. So, how many atoms are in that 1 mole? Well, 1 mole of anything is always going to be 6.02 times 10 to the 23rd atoms. Doesn't matter what it's a mole of. I could have given you 39.098 grams and asked you how many moles that was, or asked you how many atoms that was of potassium. Then you would have looked on the table, saw that 39.098 grams is the mass of 1 mole of potassium, and then you would have known that that's how many atoms there are. There's 1 mole, 6.02 times 10 to the 23rd. Next question asks us how many moles are in a 36-gram sample of water. So first thing that we really need to do for this is figure out how many grams are in 1 mole of water, aka find the molar mass of water. So we're going to need our table of elements. We're going to have to look up the masses of the components in water. Now water is H2O. So, hydrogen, if I look on the table of elements, that's atomic number 1. It weighs 1.008 grams. I'm going to go ahead and just call that 1, okay? We also have oxygen. Oxygen weighs 15.999 grams per mole if you look on the table of elements, but I'm also going to round that off to 16. So, in our water molecule, we have H2O, so that means there's 2 hydrogens and there's 1 oxygen. So I'm going to multiply these numbers by how many atoms there are of that particular atom. So for hydrogen, there's 2, so 1 times 2 gives me 2. For oxygen, there's 1, so 1 times 16 is still 16. So whenever I add these up, that'll give me the molar mass of 18 grams per mole. So 1 mole of water weighs 18 grams per mole. Now, I got to figure out how many moles are in 36 grams. So there's 2 ways you can do this. One, you can set up a ratio. So I know that 1 mole of water weighs 18 grams. And I'm trying to solve for how many moles are in 36 grams. So I cross multiply, I get 1 times 36 is equal to 18 times x divided by 18. And 36 divided by 18 is 2 moles. You also could have just saw that 18 times 2 is equal to 36. So if that was obvious to you, you would have known that 18 is the mass of 1 mole, and if I double that, I would get 36. So that means that 36 grams must have 2 moles of water. Next, how many atoms are in 2 moles of hydrogen? So, again, 1 mole, if anything, is 6.02 times 10 to the 23rd. 2 moles is twice that much. So 2 moles is going to be 12.04 times 10 to the 23rd. Again, 6.02 times 2 makes 12.04. So 2 moles is equal to 2 times 6.02 times 10 to the 23rd, which is going to be equal to 12.04 times 10 to the 23rd. This number right here is the same thing as this number. Okay, those are both the same number. The only difference here is that this is to the 23rd, whereas this is to the 24th, but the decimal place also shifted over as well. Next topic that we covered was stoichiometry, so let's get started with those problems. First question asks us to calculate the molar mass of calcium hydroxide. That's CaOH2. Hydroxide is a polyatomic ion, and that 2 after the hydroxide tells us that I've got 2 hydroxide molecules for every 1 calcium atom. So everything inside those parentheses is doubled. So let's take a look at the atoms that we have. We have calcium, we have oxygen, and we have hydrogen. Now for calcium, there's no little number behind it, so that means that I just have 1. For the hydroxide, I've got a 2, which means everything inside is doubled. So instead of having 1 oxygen, we actually have 2. Same thing goes for hydrogen. Now I'm going to have to look up the molar mass, or the atomic mass for each of these using the periodic table of elements. So if I look these up, I see that calcium is 40.08. I'm going to go ahead and round that off to 40. We also see that oxygen is 15.999. I'm going to round that to 16. And hydrogen is 1.008. Again, I'm going to round that to 1. So, in order to solve this, I'm going to multiply these things together here. So, 1 times 40 makes 40. 2 times 16 is going to give us 32. And 1 times 2 gives us 2. So, I'm going to add these up. 40 plus 32 plus 2, which is going to give me a grand total of 114. And my units are going to be grams per 1 mole. So if I have 1 mole, that's 6.02 times 10 to the 23rd calcium hydroxide molecules, it's going to weigh 114 grams. So the next question asks us to calculate the percent by mass of oxygen in calcium hydroxide. So I'm interested in what percentage of calcium hydroxide is just oxygen. So in the last slide, we found that the molar mass was 114 grams per mole. We also saw that we had 2 oxygens, so that was the mass of oxygen, and we'd have to double that because there's 2 of them. So whenever we found the mass of just the oxygen in the previous slide, we found that the oxygen was 32 grams per mole. So now I'm going to have to go ahead and solve for the percent by mass. So percent is always part over whole. It's always going to be part over whole. And whenever you do part over whole, you're going to get some decimal answer. So to change that into percent, we have to multiply by 100%. So in this case, the part is going to be 32 grams. That's the part of the atom that is oxygen, divided by the whole compound, which is 114. Then we multiply by 100%. For these guys, these numbers that we started with, they both had units of grams per mole, but since we're dividing them, those units cancel out. So whenever we multiply by 100%, the only unit that we're going to be left with is percent. So whenever you do this algebra here, 32 divided by 114 times 100%, you get 28%. So 28% of the mass of a mole of calcium hydroxide is going to be just oxygen. So that's 28% oxygen. So here I have a reaction between calcium hydroxide and hydrochloric acid. This is actually a neutralization reaction. We're going to learn later that hydrochloric acid is an acid and calcium hydroxide is a base, and they neutralize each other. So in this case, I want to know how many moles of calcium hydroxide I need to react with 10 moles of hydrochloric acid. So here's our familiar little chart here. The first step is always to see that we're balanced. And we are. Got 2 hydrogens, 2 chlorines, a calcium, 2 oxygens, 2 hydrogens. Everything balances out on the other side. So now that we're balanced, we need to start filling in these squares on our little chart here. So the first thing we need to figure out is what we are given. So if you read the problem, it says how many moles of calcium hydroxide are needed to react with 10 moles of HCl. So the only number that we're given in that is 10 moles of HCl. So in here, I'm going to write our given, 10 mole of HCl. The reason I'm not using this box up here, I was given my units in moles. Remember, this is the box that's for grams of given. I wasn't given grams, I was given moles. So I do not need this top box here. All right, now we gotta look at where we want to go. It says how many moles of calcium hydroxide. So in this case, our wanted is going to be calcium hydroxide. So remember, the top box is for grams, the bottom box is for moles. I'm looking for moles, so I don't need this box. So I want to figure out from my reaction, if I have 10 moles of HCl, how many moles of calcium hydroxide do I need? So this is very simple. We're going to go from moles of given to moles of wanted, and the way we do that, to go in between, we need to use the mole ratio. So the first thing we should write whenever we go to do our formula, we should always write our given, 10 moles of HCl, and it's critical that we put our units down. Without our units, we cannot figure out what's supposed to cancel. So underneath that, I always put 1. This 1 is just a placeholder. It has no units. All that it's doing is holding up that 10 moles of HCl. Serves no other purpose besides that. So now I want to go from moles of HCl, I want to go from here to here. So I want to go from moles of HCl to moles of calcium hydroxide. So the thing that's going to go on top is what we want. In this case, we want to go from moles of HCl to moles of calcium hydroxide. So my wanted goes up top. The units that are going to go on bottom are always going to be the units that I want to cancel out. So I'm going to have to take my 10 moles of HCl from here, and I'm going to have to move it down over here. So I'm just going to bring that down. It's just going to be mole of HCl. All right, we call this thing that we have here, we call this the mole ratio. And the mole ratio comes from the balanced equation. So in this case, we're going to look at our balanced equation. The two things that I'm interested in are HCl and calcium hydroxide. So in front of the HCl, we have a 2. So that means that in this reaction that I need 2 moles of HCl. So again, that's going to go right there, 2 moles of HCl. If we look at calcium hydroxide, there's no number in front of it, so we assume that there's a 1 there. So I'll put 1 on top. So then whenever I go to solve this, I'll see that moles of HCl cancels with moles of HCl. The only unit I'm left with is moles of calcium hydroxide, which is good because that's what I was looking for. So whenever I solve this, I'll do 10 divided by 2. So that would give me 5, and my units will be moles of calcium hydroxide. Next one, we have our same reaction as before, where we have hydrochloric acid reacting with calcium hydroxide. Calcium hydroxide, it turns out, is actually an antacid, and it's used specifically to neutralize excess stomach acid. So if you have an upset stomach, you feel like you have that acid sort of rising up, you would actually take an antacid tablet made of calcium hydroxide to neutralize that acid. So there's our balanced equation again. We have the 2 moles of HCl reacting with 1 mole of calcium hydroxide to make 1 mole of calcium chloride, that's salt, and 2 moles of water. So this first question is asking us to calculate how many moles are in a 10-gram sample of an antacid tablet. So in this case, this is where that Leffel layout, this mole roadmap thing, is going to come in handy. In this case, we're starting with 10 grams, and I want to calculate how many moles. So I'm starting down here at mass. I've got 10 grams of calcium hydroxide. And I want to go to moles of calcium hydroxide. So this is just going to be one step. I'm going to go from mass to mole, and I'm going to do that using the molar mass. So we always start with what we are given, 10 grams of calcium hydroxide. And I always put on bottom a 1. Again, that 1 does not have any units. It's just a placeholder. Its only job is to hold up that 10 grams of CaOH. So I know this is going to be one step because I'm just going to go from mass to mole. That's just one step. So I know that I want units of mole because it asks for moles. So mole of CaOH is going to go on top. On bottom, I'm going to put what I'm trying to cancel out. In this case, I'm trying to get rid of grams of calcium hydroxide. So in order to solve this, I've got units of grams and mole. So anytime that we have grams and mole together, we call that molar mass, which we know is the mass of 1 mole of that substance. Earlier on in our slides, we calculated the molar mass of calcium hydroxide, and we found that 1 mole of calcium hydroxide, 6.02 times 10 to the 23rd atoms, molecules of calcium hydroxide, weighed 114 grams. So whenever we go to solve this, we're going to see that grams of calcium hydroxide cancels with grams of calcium hydroxide. The only unit I'm left with is moles of calcium hydroxide. So I'm going to do 10 times 1, which is still 10, divided by 114 times 1, which is still 114. So I'm going to do 10 divided by 114. And whenever I solve this, I get 0.088 moles of calcium hydroxide. So this was very straightforward. We just went from mass to moles by using the molar mass. Next up, I have the second part of that question. Again, we have our same formula here. We're still talking about the antacid calcium hydroxide, which is used to neutralize excess stomach acid. And in this case, we're going to have to do a little bit of stoichiometry here. So when studying for your benchmark, you produce 10 moles of HCl in your stomach. So maybe you're a little worried, a little stressed out, that stomach acid starts to rise. So you want to calculate exactly how many moles of calcium hydroxide you need to take in order to feel better. So anytime we do a stoichiometry problem, first step is always to check to see that we are balanced. And in this case, we are. You're given a balanced equation. Now we're going to have to figure out how many moles of calcium hydroxide I need to take. So I'm starting with my given here, which is going to be 0.1 moles of HCl. What I want to find is how many moles of calcium hydroxide. So again, I don't have any grams here. I'm not given grams. I'm not asking for grams. So that means that I do not need these top boxes. Remember, these top boxes are for grams of given and grams of wanted, but I do not need them because I'm not asking for grams and I'm not given grams. What I am given, however, is 0.10 mole of HCl. What I'm looking for is how many moles of calcium hydroxide I need to take. So this is going to be one step. I'm going to go from mole of HCl to moles of calcium hydroxide, and I do that using the mole ratio. So I'm always going to start with what I'm given. In this case, I'm given 0.10 mole of HCl. And again, I'm going to put my placeholder on bottom. That 1 does not have units. It's just a placeholder. It's only holding up that 0.1 moles of HCl. So in my next little bracket here, I'm going to want to go from mole of HCl to mole of calcium hydroxide. So in this case, my wanted is going to be mole of calcium hydroxide. And on bottom, I'm going to need to put my units that I want to cancel out. So I want to take my mole of HCl, which I want to get rid of, and put that on bottom here. So once again, I have mole and mole, and anytime we have those two things together, we call that a mole ratio. That comes from the balanced equation. So we're going to look at our balanced equation here, and the two things that I'm interested in are HCl and calcium hydroxide. So we see that we have 2 moles of HCl in our balanced equation. So put it 2 because there's a 2 in front of HCl. Then if I look at my calcium hydroxide, there's no number, so I assume that it's a 1. So once again, I'm just going to have to do 10.10 divided by 2. So whenever I do that, I get 0.05, which is half of 0.1. And mole of HCl canceled with mole of HCl. The only thing I'm left with is mole of calcium hydroxide. So my units here are going to be moles of calcium hydroxide. So if your stomach gets upset while you're studying for your benchmark, you can figure out exactly how much calcium hydroxide you'd have to take to neutralize a given amount of hydrochloric acid. The next topic that we discussed was states of matter, and this was a very short unit. First question here asks you what happens to the motion of particles as a sample of ice cools. So here we have a solid, and you can see that the solid is about 200 K right now, and you can see the particles are kind of moving around just a little bit in place. What I'm going to do now is decrease the temperature. So notice the motion of the particles. Now whenever I decrease it, you see that that motion is even less. So whenever I decrease the temperature, I'm decreasing the kinetic energy of the particles, which means that the particles move slower. So if I take this down to 0 K, which is a theoretical value, that's absolute 0, you see that all motion stops. So a student boils water inside of a can. He then inserts the can into a pan of cool water, and the can is instantly crushed. So what I want you to do is to explain to me why.
We filled this barrel with a couple inches of water, and we heated it up so as you can see it's like turning into steam. And then we're going to quickly put this can filled with steam into the bucket of ice water, and it should crush. That's because it's going to go through a rapid phase change where the steam is going to condense quickly into water vapor, and pressure inside of the can is going to be less than the pressure from the outside, and it should crush. It should explode.
So inside that steel drum, there's a little bit of water that they boiled, and they're putting the cap on it.
Twist.
That's hot.
She's then going to take that steel drum and put it into the cool water. Now, inside of the can is steam, so the pressure is high. When we put in the cool water, that steam is going to turn back into a liquid. It's going to condense. So there'll be nothing inside of the can, no gas inside the can to counteract the pressure of the atmosphere on the outside of the can. So, just like with our soda can, whenever that water vapor condenses, we're left with no pressure inside the can to counteract the pressure on the outside of the can. So when that water vapor condensed back into a liquid, the pressure inside of the can is less than the atmospheric pressure on the outside. So atmospheric pressure is higher, and it crushes the can. Next topic that we're going to talk about is gases. So the first question has a sample of gas, which is at constant temperature, that is compressed to half of its original volume. So I want to know what happens to the pressure and why. Here I have a sample of gas that is at constant temperature, and you can see that the amount of gas will be constant for this little video. What I'm going to do is I'm going to change the size of my box here, the size of my container, and we're going to see what effect changing the volume has on the pressure. So right now my container size is 1 liter, and I'm going to compress this gas to half its original value. So you can see right now, before I change anything, that the pressure is at 2 on our little pressure graph here. So I'm going to take my volume, and instead of being 1, I'm going to make it 0.5, which is half. And as soon as I do that, you see our graph changed. That's because our pressure is going to start to change as well. So I've halved the volume, so the gas should now have twice the pressure. And you can see now there's the pressure leveling out. So pressure and volume are inversely related, which means that if the volume is cut in half, that's cut in half by a factor of 2, then the pressure will go up by a factor of 2. So 1/2 is the inverse of 2, so we expect that for half the volume we would get twice the pressure. Next up, the question asks about the air inside of a tire, which is at constant volume, and I want to know why the pressure goes up when friction from driving heats the tire. So first, friction heats the gas inside of the tire. That leads to an increase in kinetic energy, which means that the particles will move faster, and faster moving particles will collide more, and gas pressure results from those collisions. Here I have a sample of gas, which is at constant volume. So this could be the gas particles that are inside of a tire. As the tire rubs against the road during driving, that friction is going to cause the gas inside of here to heat up. So it's got the same effect of increasing temperature whenever we're at constant volume. So whenever I increase my temperature, you see my pressure starts to shoot up. This is because the kinetic energy is increasing. The particles move faster, so they start to collide more. And gas pressure results from these collisions. So by heating up the air in my tire with friction, I've caused that pressure to go up. Next, I want you to draw the trend on the graphs below and label with the correct gas law. So the first relationship that we have is between volume and pressure. You see that there's no temperature on this graph, therefore temperature is constant. So in that case, it's going to be that inverse relationship. So remember, for Boyle's law, we say that Boyle is a VIP. V is for volume, P is for pressure, and I is for the inverse relationship between them. This is another way of saying that if the volume is high, so here we are with high volume, that the pressure will be low. So that's low pressure and high volume at this point right here. If the pressure is high, so this is high pressure, then the volume must be low. So there's low volume. So that's what that point corresponds to. Next, we have the relationship between volume and temperature. There's no pressure on this graph, so pressure is what's constant. The relationship between temperature and volume is direct. So for Charles's law, we say that Charles watches direct TV. This is because the relationship between temperature and volume is high. So if volume is high, here we are at high volume, the temperature will also be high. Next up is the relationship between temperature and pressure. This time there's no volume, so we know that that is constant. This is again going to be a direct relationship. This is Gay-Lussac's law. Gay-Lussac directly touches people. That's how we remember. Directly stands for the direct relationship. Touches stands for temperature, and people stands for pressure. So if the pressure is high, here we are at high pressure, the temperature will also be high. Direct relationship here. I do want to point out that these don't necessarily have to be straight lines. For example, something like this, while it's not a straight line, it's still showing the same relationship. It's still showing that here, whenever we are at high volume, we're also at low pressure. And whenever we're at low volume, we are at high pressure. So it's still showing the same relationship. So even if you saw something that was like this, it's okay because that's still the correct relationship. We can only assume that this is really a straight line if we had an ideal gas, which we know there's no such thing. That's just a theory. It's a model to help us understand gas behavior. So a gas has a volume of 10 liters and a temperature of 300 K. If the gas expands to 13 liters, what is the new temperature? Assume that pressure is constant. So the variables that we have volume 1 is 10 liters, temperature 1 is 300 Kelvin, volume 1 is 13 liters, and temperature 2 is what we're looking for. We're looking for the new temperature. So in order to solve this, I'm going to need my combined gas law. It says pressure is constant, so that tells me that I can just cancel pressure out. So once I get rid of pressure, I'm left with V1 over T1 equals V2 over T2. So I got the variables T and V. So this is going to be Charles's law because Charles watches DirecTV. So now I'm just going to have to plug things in to substitute. I have my volume 1, which is 10 liters, divided by my temperature 1, which is 300. And then I have my volume 2, which is 13 liters, divided by temperature 2, which in this case is going to be X. So to solve this, I'm going to cross multiply. I've got 10 times X. It's going to be equal to whatever 300 times 13 is, which is going to be 3,900. And I got to divide both sides by 10 to cancel out the 10 here. So what I'm left with is X is equal to 390 Kelvin. So we can check ourselves to make sure that this makes sense. In this case, we have the temperature going up. So that means that my volume should have gone up. And whenever I look, my volume did in fact go up from 10 liters to 13 liters. So I would expect for my T2 to be greater than 300 Kelvin. In this case, it's 390. So that makes sense. If you got something like 30 or you got some weird number that was less than 300, you would know that you did something wrong. I would recommend that if you find yourself in that situation, you make sure that you started with the correct equation. So, next question asks about when an ideal gas behaves, when a real gas behaves most like an ideal gas. So remember, in the summer, your life is ideal. You are under low pressure because there's no school, and the temperatures are high. So being under low pressure, this means that there are lots of spaces, there's a lot of room between the particles. So there's nothing that's going to force them together and make them behave non-ideally. When temperatures are high, this means that the particles have high kinetic energy. So those particles are moving too fast to be attracted to each other. So that means that the attraction between particles is weak. So the two big things you got to remember about ideal gases is that there's lots of space between the particles and there is no attraction, or that attraction is very weak. Those are the conditions under which a real gas will behave ideally. The next question asks us to design an experiment to test the relationship between pressure and temperature whenever volume is constant. So I want to go over a few terms first. First, the hypothesis. Hypothesis is going to be an if-then style statement with a because. So I need if something happens, what will occur, and I need an explanation as to why. It's based on observation, and it's a possible answer to our research question. So let's say we were doing an experiment and we were trying to determine the effect of different colored light on the growth rate of a plant. So our research question would be, what effect does light color have on growth rate of plants? So my hypothesis is a possible answer to that question. So a possible hypothesis could be, if green light is used, then plant growth rate will be slowed because plants do not absorb green wavelengths of light. That's why plants are green, because they absorb every wavelength except for green. So that's a possible hypothesis. There's an if, a then, and a because. So it's based on observation. It's not just a random guess. It's not even an educated guess. It's a possible answer to my research question based on observation. Next are controls. Now, a control is not what you can quote-unquote control in an experiment. It is not what you can control. People always make that mistake. The control is actually what we compare our results to so we know the normal response. So in my plant growth rate experiment with the different color lights, I would want to know if a plant that grew under green light, is this growth rate less than or greater than or the same as normal? So I'd have to figure out what normal was. That would be my control. So in this case, it would be the normal growth rate of plants under normal sunlight. So that would tell me whether or not the different colors of light are having any effect on the plant. Next are constants. So I want to be sure that the only thing causing my dependent variable, causing my growth rate to change, is because of my independent variable, the color of the light. So to make sure that the growth rate depends only on the color of light, I want everything else to be constant. That means that I want the same plant, I want the same amount of light, I want the same amount of water, I want the same soil. All of these things need to be kept constant. Otherwise, if I saw that my plants grew slower with the green light, I could say, well, it's because I didn't water the plants the same amount. Maybe I watered my green light plant a little bit less. So I got to make sure I keep all of those variables constant so I can be certain that the relationship between plant growth rate and plant, the color that the plant is grown under, are the only things that are changing. Next is the data to be collected. So I want to collect the data that's going to answer my hypothesis. So my hypothesis has my independent and my dependent variable in it. If the color of light is green, that's my independent variable, then the growth rate will be slowed. That's my dependent variable. So I need to collect information on my independent and dependent variables at the minimum. In addition, I should probably collect observations if there was temperature changes or I missed a day watering or that sort of thing. Those are all things that I need to record as well. So the first thing it asks for is a procedure with controls and constants. So back to our pressure temperature experiment at constant volume. First thing I would do would be to obtain a sealed vessel. So that would be some container which is at constant volume, and it says volume is constant. So I want to make sure that whatever I put my gas in and take measurements from is going to be constant volume, and I do this by having a sealed vessel. And I want to take temperature and pressure data. That's my independent and dependent variables. My pressure depends on the temperature. So my independent variable is temperature, my dependent variable is pressure. So I need some way to measure those quantities for whatever gas I have inside the container. Next, I'm going to want to record the starting pressure and temperature. That is our control. It is the normal temperature and pressure of the gas before I make any changes. So whenever I increase the temperature and my pressure goes up, I'll be able to say it went up from the original value. I have something to compare that to. So our control is going to be the normal temperature and pressure of the gas before I go change anything. Next, I'll have to take that sealed vessel and put it on a hot plate. I just need some way to heat the gas that's inside. So the easiest way to do that is just to stick it on a hot plate. I could immerse it in hot water. I could do all kinds of things, but let's just keep it simple and stick it on a hot plate. Then I would want to record the temperature and pressure every minute. So at some regular time interval, I would record the temperature, my independent variable, and my pressure, my dependent variable. Just so I could have several data points to fully establish the relationship between those two variables. Constants. So lots of constants. I would want to have the same vessel, the same amount of gas. The volume is going to be constant. I want to make sure I make my measurements at equal intervals. All of these things can be constants. Ideally, I would do more than one trial in my experiment here, so I'd want to make sure I keep everything constant from trial to trial. So next is a hypothesis. Again, that's an if blank, then blank, because blank statement. So If the temperature of the gas increases, my independent variable, then the pressure must also increase. So that's my dependent variable. This is because at constant volume, gas particles will collide more as they are heated, leading to greater pressure. So the idea is that whenever I heat up those gas particles, they're stuck in the same volume. They have no more space to move around in. So as they are heated, they're going to start to collide more, which is going to lead to greater gas pressure. Data to be collected. So you would collect the temperature and pressure, the independent and dependent variables of the gas at every minute. And this data should be organized into some kind of data table. That way, whenever I look back, I have everything neatly organized and I'm not going to make any mistakes in interpreting that data. So the dates of the benchmark, if you are A day, it's going to be on 3/28, and if you are B day, it's going to be on 3/29, so that's next class for everybody. If you are absent, you need to plan on staying after to take the test on Wednesday, Thursday, or Friday to make it up. If not, it's going to have to go into the gradebook as 0. So if you're absent, plan on staying after one of those days. The end of the marking period is on the 30th, so we need to get all of those grades in before that date.